Hello! This video is on exponential growth and decay. We're going to start with a couple examples of exponential growth and decay. This is not on your notes, so you don't need to write it down unless you want to. Just some quick examples. Bacteria growth will grow exponentially. Finances that are in bank accounts can follow an exponential growth pattern. And then we mentioned this before the MCAs that populations also tend to follow exponential function models. So if you guys think back to before testing, we started exponential functions, and first we just learned about basic exponential functions, which look like y equals a times b to the x power. So that's the general formula. If you guys remember, the a is our starting value. So it's what we have when x is equal to 0. And then b is what we are multiplying by each time. So that has to be greater than 0. Okay, so there's going to be, I think, 4 different formulas in this video. That might seem like a lot, but just keep in mind, if you have this sheet by you, your note sheet, you really just have to follow the formula and plug in what you know for different types of problems. So the first one is called exponential growth. This occurs when a quantity increases by the same rate r in each time period t. So it's called growth because it's increasing, which makes sense. The general formula looks like y equals a times 1 plus r to the t. So y is our final amount, a is the original amount, so that's what we start with, just like in our other formula. R is our rate of growth. That's given as a percentage usually, and then we change it to a decimal when we use it in the formula. And t is time. Okay, we're going to look at an example right away for exponential growth. So we know in our problem the original value of a painting is $1,400. So that would be our A value, that's the starting amount. And the value increases by 9% each year. So it increases its growth by 9%. Write an exponential growth function to model this situation and then find the value of the painting in 25 years. So after we have our formula, that's going to be our time. So I put the generic formula at the top. We already said that we know A is 1,400. That's the initial value of the painting. We know R, which is our rate, is 9%. We want to make that a decimal, so we'll make it 0.09. We always want to work with decimals in our equations. So our general formula would just be y equals 1,400 times 1 plus 0.09 to the t. Okay, you can simplify what's in the parentheses there. So that would give me y equals 1,400 times 1.09 to the t. So that's our generic formula where we can plug in anything for time. And then this specific problem asks for the amount that the painting is worth after 25 years. So I would plug in 25 for t. So I have 1,400 times 1.09 to the 25th power. Now on your calculator, what you're going to want to do is the 1.09 to the power of 25 first. Remember, you have to use the caret key. And then multiply by 1,400. When you do that, you'll see the painting will be worth $12,072. If you round to money, 31 cents. Okay, so another thing that falls under exponential growth is compound interest. Compound interest is earned on both the original amount and previously earned interest. So for example, if you put money in an account, maybe you're saving for college or a car, if it has compound interest, you'll make money on the amount you put in originally. So maybe you put $500 in to start, plus interest you earn over time. So the general formula for this is A is equal to P times 1 plus R over N to the NT power. So a couple more variables here. So A is the balance after T time. P is the original amount. R is the annual interest rate, so again it'll be given as a percent, and we will convert it to a decimal. T is time, and N is the number of times interest is compounded. So N can vary, but N can really only be 3 different things. So N, as when we practice it, you'll see N will come from this information. You have to know if you are compounding annually. Annually means once a year. So in that case, N would be 1. N could also be compounded quarterly, which means your interest is done, or the compound interest is done every quarter. Well, there's 4 quarters in a year, so in that case, N would be 4. Or your interest could be compounded monthly. Well, there's 12 months in a year, so if that was the case, N would be 12. So when you do problems, you'll pick either N as 1, 4, or 12, depending on the problem. All right, here's an example. I already put the formula at the top. You invested $1,000 at a rate of 3% compounded quarterly. So I invested $1,000. That's going to be important. At a rate of 3%, it's compounded quarterly. Write a compound interest function to model this situation and then find the balance after 5 years. Okay, so if we're going to identify some variables here, P is what we start with. We started with $1,000 we put into our account. R is 3%, which is 0.03 as a decimal. And N, we're compounding quarterly, is 4. So at this point, we're just going to write our generic formula. So A is equal to 1,000 times 1 plus, and it's R divided by N, so I'm going to have 0.03 over 4, and it's to the N T power. I'm going to leave T blank for now because we're writing the generic formula. And then I would simplify. So if I want to simplify the inside of the parentheses, I would start by dividing 0.03 divided by 4. Okay, so that would give me A is equal to 1,000 times 1 plus. When I did that, it gave me 0.0075, still to the 4t power. And now I can add these together to give myself a little bit easier of a formula to work with. So A is equal to 1,000, and that would give me 1.0075 to the 4t. So that's my generic formula. Now I can plug in any value for time. In this problem, they want us to use time as 5 years. So I'm going to plug in 5 for t. So I have 1,000 times 1.0075 to the 4 times 5 power. So this is going to give us 20. So in my calculator, what I did is I did the 1.0075 to the power of 20 first. So I ended up having 1,000, and if you round that, you get about 1.16118. And then I multiplied 1,000 times that, which means after 5 years, if I were to not add any other money, I would have $1,161 and about 18 cents. So I made about $161 in that account without having to add any other money. Okay, so now we have to look at the flip side. We don't always grow with exponential functions. Sometimes we have decay. So this occurs when a quantity decreases by the same rate r in each time period t. So it's really like the opposite of exponential growth. Instead of getting bigger, we are going to get smaller. So the generic formula will look very similar to exponential growth. We'll have y equals a, and then in the parentheses we have 1 minus r instead to the t power since we are losing something. So y is still our final amount, same as with exponential growth. A is still the original amount. R is rate of decay. Again, that'll be given as a percentage and we'll change it to a decimal. And t is time. Okay, so we're going to do a couple examples. The first one is just evaluating a function. So it says find f of 3 and f of negative 2 for the equation f of x equals 1,000 times 0.77 to the power of x. So we know this is exponential decay because the number in here is less than 1, which means our function will be decreasing. If they say find f of 3, I just have to plug in 3 for x. So I would have f of 3 is equal to 1,000 times 0.77 to the 3rd power. So on my calculator, I would do 0.77 to the third power first, multiply by 1,000, and I would get 456.53. Same thing for f of negative 2. Might be a good idea to pause the video and try this on your own. So I have 1,000 times 0.77 to the negative 2. Simplify that. I get f of negative 2 is 1,686.63. Notice it got bigger than our original amount of 1,000, but that's because we have a negative exponent. Okay, second example says the population of a town is decreasing at a rate of 1% per year. In 2000, there were 1,300 people. Write an exponential decay function to model the situation, and then find the population in 2008. So again, important information, it's decreasing at a rate of 1% per year. We started in 2000, and there were 1,300 people. Write an exponential decay function to model this situation. So we have it up top, y equals a times 1 minus r to the t. In this case, let's follow along. So we have y equals a is my beginning amount, which is 1,300, times 1 minus our rate, which is 1%. Make sure you change it to a decimal, so 0.01 to the t. Can simplify that, so I get y is equal to 1,300 times 0.99 to the t power. So that's our generic function for this situation. Notice the number in my parentheses here is less than 1 because our population is decreasing, so it has to get smaller. So if they want the population in 2008, t would be equal to 8 because the population was originally in 2000. So I'm going to plug in 8 for t. So again, on my calculator, I would do 0.99 to the 8th power first, and then multiply that by 1,300. And at that point, we have, on the calculator, I got about 1199.56. I would round down and say about 1,199 people remain. All right, so under exponential decay, we also need to talk about half-life. Half-life is the time it takes for 1/2 of the substance to decay. So this is really common when we look at like bacteria, things like that in nature. The general formula says A equals P times 0.5 to the T power. With half-life, this is always going to be 0.5 because we're doing half-life, and half is 0.5. So A is your final amount, P is your original amount, and T, this is the one kids tend to forget, is the number of half-lives in a given period. So we're going to look at a couple examples to see how this works. Okay, first one says fluorine 20 has a half-life of 11 seconds. Okay, so we care about this information. It's got a half-life of 11 seconds. We have to know how long a half-life is. Find the amount of fluorine 20 left from a 40-gram sample after 44 seconds. So if I look at my equation, P is my starting amount. So I started with 40 grams of that substance. And then T, if you think about T is the number of half-lives in a given period. So if 44 seconds passed, I have to figure out how many half-lives occurred in that time period. So I take the 44 seconds, divide it by how long one half-life takes, so 44 divided by 11, and that tells me that T is equal to 4. So there were 4 half-lives in that period. Plug in what I know, so I get A is equal to 40 times 0.5 to the 4th power. Can simplify it in my calculator, and I'll find out that I have 2.5 grams left after 4 half-lives. All right, part B, find the amount of fluorine 20 left from a 40-gram sample after 2.2 minutes. So again, starting with that 40-gram sample, after 2.2 minutes passed, round your answer to the nearest hundredth. So half-life of fluorine 20 is still 11 seconds. P here is still 40 grams, so we're starting with the same amount. Here you have to be careful. They say after 2.2 minutes, but our half-life is in seconds. So we need to work in the same units here. So I would convert the 2.2 minutes to seconds, so multiply by 60, and I get 100 132 seconds. So now I can calculate my t. So I'll take 132 seconds divided by 11 seconds per half-life, and I get 12 half-lives. Now I'm going to go ahead and simplify this in my equation. So I get A is equal to 40, my initial amount, times 0.5 to the 12th power. So go ahead and simplify that in your calculator. Okay, and you would get A is equal to 0.0098 grams. So not a lot left at that point in time. And then if we're going to round to the hundredths, we would say about 0.01 grams. Thanks for watching, guys. Please make notes of anything you have maybe questions on in these notes so you can ask in class on the block day or when we work on this later this week.